Hi, so today I want to look at the electrophilic aromatic substitution reactions of monosubstituted benzenes. So a monosubstituted benzene is a benzene ring that has something already attached to it. So this is a monosubstituted benzene ring. So it has a group already attached to the benzene, and it can still react under electrophilic aromatic substitution reactions. But before we go into the reactions, we should talk firstly about the positions in relation to the one that's already attached. So we have ortho, meta, and para positions on the benzene ring. So the ortho is the one directly next to the group that's attached. The meta is one over from that, and the para is the opposite. So one way to remember it is the ortho makes a O, the meta makes a big M, and the para is, you could draw a big P in there, but it's just directly opposite. So this one here is also a meta, and this one here is also an ortho. So we've got two ortho, two meta, and one para position on this benzene ring. So now this benzene ring that has a group already attached will be directing the incoming groups, so those electrophiles that are adding on to specific positions based on how that attached group affects the delocalized system within that benzene ring. So if a compound is electronegative, it will be adding benzenes into that benzene ring. So if it's got lone pairs on it, it can add them in. If it's electronegative, then it can activate that ring a little bit more too. So groups that activate are NH2s, OHs. They're more reactive than the normal benzenes. If you have a halogen attached to it, it's slightly less reactive than a normal benzene. And if you have a delta positive directly next to the ring, it's very deactivating, so it really slows down the reactivity. Now, let's say this is a halogen. A halogen is an ortho-para directing. So ortho-para directing. It's less reactive than normal benzene, but say we have a Friedel-Crafts alkylation. So we have a Friedel-Crafts alkylation reaction. We're adding in a CH3. That's my electrophile that's produced. The AlCl3 is my catalyst, and the benzene ring is my nucleophile. So remember, the electrons move out of that benzene ring, attach the electrophile, and then we have a nucleophile that removes the extra proton. So if you don't remember that reaction, have a look at my other video and it can refresh you on that mechanism. So when this reaction occurs, you will have this X directing this incoming electrophile into either the ortho or the para position. So the ortho is this one here, and the para is the bottom one. So there are two ortho positions on this ring, and that may mean that you get more ortho product than para product. So your two products would be the ortho substituted and the para substituted. Now, if you have something that's got a delta positive that's sitting right here where this X is, or it's got a actual positive charge, it would be a meta directing deactivator. So all of the incoming groups would be coming in that meta position. So when you're looking at these, have a think about what kind of compound, what sort of functional group is attached. That is going to direct the incoming group. It doesn't matter so much what the incoming group is, it matters what's attached to that benzene ring. It's going to change the way that delocalized system is able to nucleophilically attack the electrophile. So with this one here, I've got a disubstituted benzene ring that I'm starting with rather than a monosubstituted. So when I'm looking at what position this bromine electrophile is going to come in at, I need to take into account what's already attached to the ring. So this oxygen has a lone pair on it. It's an ortho-para director. This CH3 So the carbon group is also an ortho para-director, and both of these groups are more reactive than benzene normally is. So they're both going to be positioning the incoming group in an ortho or a para. So OH is more reactive than CH3. So the OH will have more influence on that incoming group. So ortho-para to OH would be this one here. So this group here, and para is already taken by the CH3. So the bromine would more likely to come in on that ortho to the OH. Now, some questions you might have one that's ortho-para directing and the other one's meta. So then you don't need to look at the reactivity of both of those groups that are attached because there will be one clear answer. Now, when you have competing groups with the competing way that they direct that incoming group, you need to look at the reactivity. So thank you for watching my video, and I'll see you next time.